Assalamu alaikum. So today we'll solve the first exam and we'll start with the first question, the multiple choice. Here we have 100 volt, 1000 RPM separately excited DC motor with given RA, and it take armature current of 15 ampere when driving a rated torque. And this machine is controlled by armature voltage control, which means that the flux is constant, and we need to calculate the speed in RPM in the forward regenerative braking. The forward regenerative braking, this means that the speed is positive while the current is negative given the voltage VA. So the first thing, from the rated condition we can calculate K phi, which will equal VA minus RA IA over N. Here I will use N because it's given in RPM. And if we do the math, this will equal to 100 minus 15 over 1000. So this will equal 0.085. This will be volt per RPM. So now let's come here. So the voltage is given 90 volt, which will equal to regenerative braking and driving half the load. So this will be minus 0.5 multiplied by the full load current, which is the 15, multiplied by the resistance, which is the 1, plus 0.085 N. So this will be N will equal to 97.5 over 0.085, which will equal, if we do the math, the 1147. The second one here, the armature voltage in volt required to run the motor in the reverse direction. So motor in the reverse direction, this means that the speed is negative and the current is negative. Driving the rated torque and 0.6 the rated speed. So VA will equal minus 15 the rated current multiplied by the 1 the resistance minus 0.6 multiplied by the rated speed 1000 multiplied by K phi in volt per RPM 0.085. If we do the math, then VA will equal to minus 66. So the answer here will be C. For the third one, for the motor load system, if we have T is the motor torque, TL is the load torque, and here we are giving two statements. The first one, if the motor torque greater than the load torque, the drive deaccelerate. This is not correct. Now if the load torque greater than the motor torque, the drive deaccelerate. This is correct. So the first one is not correct, the second one is correct, so the answer will be C. The motor drive a passive load is said to be a steady-state stable F. We know that partial TL by partial omega, if greater than partial TE by partial omega, the drive will be stable. So this means that partial TL is greater than partial TE, or if we do the approximation, this means that delta TL must be greater than delta TE. So this will be the answer will be B. For the fifth question, for the separately excited DC motor, a 20% reduction in the field flux, then the percent increase in the no load speed will be. We know that omega naught is proportional with V over flux. So this means that omega 1 over omega rated will equal to, the voltages are the same because we are in the field weakening, and here I will say phi1 over V over phi rated. So this will be phi rated over phi1. Now phi rated is 1, phi1 is 0.8 ampere units, so this will equal 1.25, so the increase is 25%. So the answer would be B. Now for question number 6, we have a series motor with a total resistance of 0.25, drives an elevator load of 200, which means that here the load is constant. If the motor draws 40 ampere and runs at 40 radian per second, we need to find the armature voltage. Now here we have a series, which means that IA will equal to IF. So this means that the torque is equal to certain constant multiplied by IF IA, and the back EMF is equal K multiplied by IF omega. So let's find K. So from the torque we know that T, which will equal to 200, this will equal K multiplied by IA equal to IF, so 40 square. So from here we can find K, which will equal to 0.125. So now VA will equal R total IA plus K IF omega. R is given 0.25 multiplied by 40 plus the K 0.125 multiplied by the current IF 40 multiplied by the speed 40. If we do the math, this will be the 210. Now the last one here, the selection of the power converter in the modern electric drive system will depend on. Now if we notice here, the power converter is in between the supply and the electrical machine. So this is the electrical machine and this is the supply, and this is the power converter. So the selection of the power converter will depend on the type of the supply and the used machine. So the type of the supply and the type of the motor, so the answer will be D. Now for the second question, give one example of each of the following mechanical loads and plot the power, speed, torque characteristic. Here we have three torque speed characteristics. The first one for the constant load, which is for the, let's say call it this one A, and A here is for elevator, and let's call this one B, and this one is fan load, and the last one let's call it C, and C, an example for that is the drilling. Now for the A, the torque is constant proportional with C, so the power will equal the T multiplied by the omega, so the power will be proportional with omega. So this one will be the A. For the B, we know that here the torque proportional with omega square, so the power will be proportional with omega cube. So this is the B. For the C, we know that here the torque is inversely proportional with the speed, so the power will be proportional with a constant C, so the power will be constant. So this is the C. Now for the last question, the current speed characteristic of an armature voltage control DC drive is shown below, and we need to find some unknowns. Now here armature voltage control, which means that VF is constant. So here VF in per unit, it will be 1. Whatever VF in the curve, it will be 1. Now the first thing here, for example, given for this torque speed characteristic, we have the voltage here is given, the no load speed here is given, and the I start here is given. So from here we can calculate RA, which will equal V over IA at start. So this will equal 100 over 50, and this will equal 2 ohm. So RA here equal 2 ohm. Again, we know that omega naught is equal V over K phi. So this means that K phi will equal to V over omega naught, and this will be 100 over 100, and the answer will be 1. Here this 1 volt second per rad. So here this is 1 volt second per rad. Now we need to find the voltage at this point. To find this one, we need to find omega here. Now omega here, the voltage is given. We know that omega will equal VA minus RA IA over K phi. So this will equal 100 minus RA is 2 multiplied by IA at this one is 20. So this will equal 60 volt. This will equal so 100 minus 2 multiplied by 20. This will equal 60 rad per second. Now at this point we know that V should equal EA, the back EMF, because the current here is equal to 0. So V will equal 60 volt because K phi is equal to 1. So this one is 60 volt. Now we need to find, for example, V2. Here the current in regenerative braking, it's minus. The speed at this point, we know it. The speed at this point is 60. So we can calculate V2. So V2 will equal minus 7.5 in the regenerative braking multiplied by the resistance 2 plus K phi, which is the 1, multiplied by the speed at that point, which is the 60. If we do the math, this will be 45 volt. So V2 will equal 45 volt. Now this one here is easy to calculate because at this point we know that omega will equal V2 over K phi, and this will be also 45 rad per second. So the speed omega naught will be also 45 rad per second. Now we need to find omega. Now the voltage is given, which is the 45, which will equal 2 multiplied by the current at the point B, which is the 20 plus K phi, which is the 1, multiplied by the omega. So omega here will equal to 5 rad per second. Now if we need to calculate I2, then I2 will equal V2 over RA. This will equal 45 over 2. So the answer would be 20.5 ampere. If we need to calculate the efficiency, we know that the efficiency is equal P out over P in. Now P out will equal the torque multiplied by the speed, and Pn will equal Va multiplied by Ia. So this will equal to the torque at point B, because the K phi is equal to 1, then the torque will equal to 20 Newton meter multiplied by the speed, which is the 5 over V2 was 45 multiplied by the current, which is 20. If we do the math, this will be equal to 1 over 9. So the efficiency here is 1 over 9. The value of VA that will put the motor in stall condition. Now we know that the load is constant, so this means that if we put the torque speed characteristic to intersect with a 20, then the machine will be in the stall condition. So here this means that VA will equal 20 multiplied by the 2, which is the 40 volt. That's it. Thank you.